Aaron, can you hear me?
I can, but you kind of sound like a robot.
I sound like a robot?
Yeah, it sounded all like digitized.
Oh, goodness.
It might just be the connection.
Yeah. How's it going?
It's going. We just had Itza's thing, and it was just bad. Like you couldn't see his board, but you could see him. You could hear him, but you couldn't. Like his board was all blurry. He said he's going to take pictures of it, and I messaged Callie, and she said that she had the same problem.
Now, wait a minute. Hold on. Since you said that, because I'm going to ask you. Wait a minute. Let me move my camera. Can you see my board? Can you see that?
This is better. I don't know whether it's your computer setup or it's the program, because he didn't use Zoom. He used conference through Canvas. I can see what's going on there, but with his, the blackboard was it was blurry, like it was underwater.
Okay, wait a minute. Let me grab I'm trying to make sure, because I set mine up to make sure people could see me just in case if I needed to, right?
I like your setup. It looks like a really cute office. I like it.
Thank you. Well, this is well, I tried the best I could. Other than I got kids in the space, they got their table here. So, wait a minute. Can you see me and can you hear me? Can you see that?
I can hear you and see you, but that's honestly blurry. I can tell like real faint. Like it looks like I'm drunk. It says 2H2 plus I don't know what.
Okay. I may need to write it bigger. It's okay. That's what I'm trying to see. I was writing the equation for water.
Yeah, I kind of thought that might be what it is, but I can just, like I said, it looks like I'm looking through drunk goggles.
Wait a minute. Hold on. Let's try it this way.
That's a little better, but still it's blurry. Now I can't see anything past plus, I think it says plus O2.
Yeah.
I can't see anything past that except it's just blur. And I don't think it's necessary to glare off your light.
Okay. I'm trying to see. I'm playing with light. That's what I'm doing to try to make sure it's not as blurry. Okay.
Sure.
All right, but I'm gonna angle this back down toward my chair. Yeah, that's what I'm gonna probably do. What I'm gonna probably do is zoom in and because I can move my camera and then mount it toward the board, so it's not a problem.
Sure.
Yeah, that's all. It's just me moving. All right, let me find who else is on? Hey, you guys. Hey, Jenna. You in Texas? Jenna, can you hear me? Let me do something. Let me open up my chat window. Okay.
Her microphone's off, Dennis.
Okay.
Do I need to?
There you are.
Okay. I was just trying to see if you can hear me. I still have your book. Text me your address so I can mail it to you. I got it at the house.
Okay.
I got it. Like, yeah, actually I do. It's right here. I have your book. So I can mail it to you. So send me your address so I can mail it to you. So.
Okay.
Because I was like, oh my
All right, yes,
God, this is hard. So I'll text it to you.
Okay.
Liv, hey. Okay. While y'all are all coming on, how was physics, you guys? Ooh, I'm scared to ask. How was physics? Okay. Don't say anything.
It's hard to see the board. I don't know about anybody else, but it was a blur.
Okay.
I was not paying attention.
That's not good. Okay. I don't need you to be like that.
He was teaching on stuff that wasn't on our test.
Oh, okay.
Yeah, true.
We're on chapter
Today would
15.
have been a better day for like having.
We're on chapter 15, right? You guys, chapter 15?
If you say so.
Chapter 15, you guys?
Sure.
Are you serious? She's like, sure. Okay.
Travis said that his Wi-Fi is broken, but he is attempting to get on.
Tell him to download it through the app on the phone. You can put Zoom on the app on the phone. It's a Zoom app. All right. Okay, you guys. I am still here. I am going to go fix me some lemonade so I can have something to drink. And then we're going to start on chapter 15. I got your test graded. I'm going to put that. Now, my internet, because I have satellite and it's cloudy today, it may go in and out. Just stay on. It's fine. It'll just pop up and say, your internet connection is unstable. It's just because it's cloudy today. I'm going to get me some lemonade, and then we're going to get started.
Hey, Liv, do you see where we're going to try to do voluntary labs for growth?
Yeah, what does that mean?
It means he can't tell us that we need to be there because of liability, but if he can get it approved, the three of us, along with him, will show up and try to finish out the work that we've got left. Of course, we can't
Okay.
or anything like that, but we can at least do the physical work. And he said maybe pick one day a week, whatever works for the four of us.
Yeah,
And
that works.
finish up the systems and work for several hours and just knock it out. And then he'll give us quizzes and tests from there. And of course, he'll be in front of us so that he can do his lecture like he will do like on the board.
Yeah, y'all can practice social distancing. That'll be kind of hard.
Sorry, ma'am.
I said, you guys can practice social distancing. Y'all can spread out in
That's
there.
what we're doing exactly.
Katie, hi. Hey, Tara. Did you get my message? She got it. Tara said, hey, I can't see your class. So I was like, okay.
Well, yeah, I guess because I'm on it now. Yeah.
You guys, I am recording this as well. So if you don't pick up everything, you forget something or other, don't worry about it. It's recording for people who can't get it. Labs, I know that is a big question. this is what we're going to do. Like I just told the other class, I'm going to keep it as normal as possible. What I am going to do, I found some of the labs on YouTube. So whatever labs we have not finished, what I'm going to do is go onto that lab, put a link on there. You just view the lab, write it up just like you were there, and just write it up. Your lab practicum, the same thing. Just look at the lab that I tell you to look at and research it and go on as normal. That's what we're gonna do. The only difference that I am going to do is for us is that our test's gonna be online. That's it. We're gonna still have chapter quizzes, all of that stuff. So the only thing is our test's gonna be online. They do have to be timed. So they can't be open. That's one of the things they did tell us, that if we give exams online, they have to be timed. And I think that's pretty much it. So I'll put up the links to the labs, and I'll put them in the announcement too. I'll probably just write one announcement with the links to all the labs. I will open them if you want to go ahead and write all of them up and have them done already. Totally fine by me. If you want to do one every week, that's fine by me too. I'm just going to keep it on the same schedule. So is that okay with you guys?
Sure.
Okay, so
Dr. Jones, is our final still gonna be like the same?
that is what me and Dr. Craig is trying to figure out now. Because the ACS crew do not have an online version of the exam, they just don't trust it. They're a little old school. They have an online version, but they like the online version to be in a classroom or a computer lab. That's the way they got it set up. Let me set my camera up a little bit, sorry. Yeah, I got a board in the back too, so. We're trying to figure that out. So they sent him an email, and what he said that he's going to do for me is he's going to look at the test. Like I said, I can't look at the test. I don't even want to look at the test. I just don't. But what he's going to do is send me a copy of topics, a list of topics that are on the test. And then from there, I have to make up the questions based on those topics. Now, what I am going to do is the exams that we have already taken, I am going to look at those exams, and if the topics are there and everything, you're going to get questions very similar to what you had during the semester. That's what I'm going to do. So I'm going to try to match it up and make it look as close to an exam as possible. So that's what I'm going to do. So as of right now, I'm going to be making your final exam. Like I said, I'm just, once he give me the topics, I'll go from there. So that's all I know about that. So other than that, everything else, I'm going to try to keep it pretty much the same. The only difference is we're just not meeting in person. So it'll be easier on you, it'll be easier on me, and that's how it's going to go. I know some people are posting stuff during lab time. You guys, your time, manage it wisely. That's what I'm going to tell you. Like I said, you can sit down and look at all the videos, write your reports up. Like I said, you can do that every week. You can do that whenever you want to. That's totally up to you. So, hey, Sydney. Totally up to you. So, no matter how we do it. Okay, so while we doing that, I got lemonade. Let's get started. We're gonna do, can everybody see chapter 15 on your screen?
Yes, ma'am.
Yes,
Yeah.
ma'am.
All right, let's get started. All right. Okay, so chapter 15, bending. So our next test is going to be on 13, 14, 15, and 16. Your homeworks for you guys. I think I should have already put your last set of homeworks up there. What I am going to do extra, since we are online, there's some other topics, the carbonyl groups and the all of that. Those are going to be a separate thing. Now, looking at if those are one of the topics on the exam, because what I'll probably do is give him the chapters and topics up under the chapters and see if those are on the test. That's what I may do to make it easier for Dr. Craig. If they are on there, it is basically chapters for that fourth test. It should be 17, 18, and 24. And then it should be chapters 19, 20, 21, and 24. Those chapters all deal with carbonyl chemistry and all of that. Usually those topics are on the test, so that'll be a bonus test for you guys that are there. So you just have an extra test. Now, as far as lecture are concerned, for that, I'll probably go ahead and pre-record those and just post the lecture so that you guys don't have to worry about sitting and listening to me that way. I'll just go ahead and record those. So that's what I'll do for that. Because I just want to make sure that I cover all the topics that is supposed to be on the test. Because Dr. Craig wants me to make sure that I make the test as close to what is to simulate what you guys are going to have. So I want to make sure of that. So that's what I'm going to do. All right, let's get started. Chapter 15, benzene. So benzene is a simple aromatic hydrocarbon. They call those arenes. So sometimes when you see functional groups, they are listed on there. Now, benzene have 4 degrees of unsaturation, making it is a highly unsaturated hydrocarbon. Now, this is the thing with benzene. When it undergoes addition reaction, you have alkenes and alkynes that undergoes those reactions. The dienes readily undergo that. Benzene does not do that at all. It doesn't do an addition reaction. It likes being in its ring, but there's something else it likes to do. I'm trying to see. Wait a minute. Okay, there we go. Let's put this. All right. Now, what benzene really do like to do, it likes to basically do a substitution. It doesn't like addition at all. It likes to substitute. So let's just say if you reacted like this and you reacted with bromine, what happens is when you react it, one of the hydrogens get replaced with bromine. So it does not like any type of addition. It likes to do substitution. So what it does is take a hydrogen off and replace it with something else. That's what benzene likes to do. Now, Kekule proposed that benzene was a rapid equilibrating mixture of 2 compounds, and it contained these 6-member rings with 3 alternating bonds. Hey, you guys, somebody don't have their mic muted. Can you mute your mic? I think that's what the feedback.
Okay, sure.
Okay. Now, with that, basically what he was saying is that sometimes you have a single bond and a double bond. And what it is, it forms this equilibrium. Basically, those double bonds can be anywhere in that 6-member ring. And so basically, it's a resonance structure. That's what he basically said. Okay, that's what he found out. Is equilibrium is a resonance structure, and they call Kekulé structures. That's what it is. Now, when you look at benzene, you got to account for certain things. 6-member ring, 3 additional degrees of unsaturation, is planar, and all the bonds have to be equal length. Now, the Kekulé structures have to satisfy the first 2 criteria, but sometimes it don't have to satisfy the third one. Now, you can have them that it can have short bonds, they can have longer bonds, and all of that. But that's what they look for when you have a benzene structure. You got to have the 6-member ring, and it got to be planar. That's the main 2 things they look for. But most of the time, most people draw them, they draw them as the bond lengths being equal. Now, what about the hybrid of benzene? Because you know how we draw benzene. We draw it with a little circle in the middle of it. And so that's why, to show that it has that resonant structure. And so the true structure is a resonant hybrid of 2 Lewis structure with dashed lines of the hybrid indicating the position of the bonds. Usually what they do, they use one of the 2 Lewis structures and not the hybrid. What they try to do that is to keep track of the electron pairs. That's why they do that. Now, okay, so with this, you got pi bonds, and pi bonds have those 2 electrons. Benzene has 6 pi electrons. So what they do is, like we said here, they draw it as a hexagon with a circle in the middle, and the circle represents the 6 pi electrons, distributing one of the 6 atoms over the ring. Now, let's talk about this. Now, they say the bond length is 1.39 angstroms. So 1.39 angstroms is, what is that, 13.9 nanometers. That's what they're saying. So the carbon-carbon single bond is 1.53 angstroms, and the carbon-carbon double bond is 1.34 angstroms. So about the same, not too much off. So that's what they're saying. That's the actual bond length. Sun, please come out. Okay, each carbon atom in the benzene ring is surrounded by these 3 atoms. Now, it's trigonal planar with the bond angle. So if you have your molecular model, that's what you see over there in your bottom left corner. It's planar. And then what they show is sp2 with the p orbital. So that's how it actually looks. So each carbon has a p orbital with 1 electron that extends above and below the plane of the molecule. So the benzene ring sits on one plane, and then that's where the p orbitals extend from. So at the top and the bottom of the plane. Now, overlap of these p orbitals creates 2 rings of electron density, and that makes sense. You got electron density at the top, you got a lot of electron density at the bottom. Now, with that, it makes the benzene electron rich and reactive with strong electrophile. So basically saying it won't do the addition, but it'll do the substitution. So that's what it is right there. So that is the main reason. Now, when it comes to benzenes, there are a lot of them out there. So these are some common ones here. So you got ethylbenzene, tert-butylbenzene, chlorobenzene. So you name the benzene ring with one substituent, name the substituent, and add the word benzene. Now, you got a lot of them that are monosubstituted benzenes that have common names. Okay, you should know those already. So toluene, that's really just methylbenzene. That's all what toluene is. It's just benzene with a methyl group on it. Simple as that. Phenol, it's just hydroxybenzene. That's all what it is. It has a OH group. Aniline is aminobenzene. It's just one with an NH2 group. That's all what it is. So a lot of the benzenes that you see and name, they just have that mono substitution on there. But a lot of times you'll see them, they have benzene at the end. Now, I think this is one of the things in organic that I love to hate and I hate it to love, was the nomenclature when it came to the benzene derivative. Now, they can be attached in several ways. You got ortho, meta, and para. Now, you got to know the difference between the two. Now, ortho means they are basically side by side. So one at the top and one right here on either side. Now, you can have the meta, which is basically one is still up at the top. You skip one and it's one right there. So that's really what meta is. And then you have para, meaning that it's one straight up at the top and one straight at the bottom. So that's really is not that easy, but you can have them to be there. So you got 1, 2, 1, 3, and 1, 4. So just remember that you got 1, 2, 1, 3, and 1, 4. So that's how they do the nomenclature of the benzene derivatives. Now, if their two groups on the benzene ring are different, you got to alphabetize their names. Y'all have heard this before you put the word benzene. So let's take a look. So you got O, bromochlorobenzene. If you got that, you got M, fluoronitrobenzene. And then, or you can use a common root name. So you got P, bromotoluene, or O, nitrophenol. So that's how you have to name those. So you either have to put the O, the M, or the P in front of it, and then whichever group that is in alphabetical order first, you name that first, then you put benzene at the end, or the other common names of the benzene at the end. Now, for 3 or more, you got some of them that can be long. The number is given to the lowest possible number around the ring. You still alphabetize or put them in order, the substituent's name. And if they are part of the common root name, name the molecule as a derivative of that monosubstituted benzene. So they got 4-chloro, 1-ethyl, 2-propylbenzene.
Tasteless.
Huh? So 4-chloro, 1-ethyl, 2-propylbenzene. And then over here you got 2,5-dichloroaniline. And so for that one, whichever one that is closest to that top, that's where they want you to start it. So like for the first one, for 4-chloro, 1-ethyl, 2-propylbenzene. So what they did was the ethyl group is closest to that para position, that top position. So that's where they started with 1, and they did it that way. Now in the second one, what they did, they started with the para, and then that 1 at the top, and then they moved 2 right there to the next one, and then 5. So it just depends where you give the lowest possible number, but they're gonna try to start with it up there at the top. That may be an email coming in. Sorry about that. Okay, now, what about benzene as a group itself? Now, a benzene substituent is called a phenyl group, and it can be abbreviated as pH. So you can have phenyl groups. So the phenyl group is C6H5, and then whatever else is attached to it. Now, so what can you do? You can abbreviate it as P's, small h and H, and the phenol itself will PHOH. So you can abbreviate it. Why do that? where you can just write the name out, but you're only missing 2 letters. But sometimes people like to write shorthand, and that's what they use. Now, what about benzyl groups and aryl groups? So with that, the benzyl group contains the benzene ring. It's different from the phenyl group. So the benzyl group will always have something else hanging on it. So the benzyl group still have your 6 carbons in the front, but like right here, they got H5, and then they put another group on it in place of that last hydrogen. That's what they do. And then that one has still space on it to add something. Now, the phenyl group right there, that's still C6H5, and then they can have something over there. Now, they are derived from other substituted aromatic rings. They're known as aryl groups. Now, so what about them and looking at the characteristic absorptions when you want to look at IR, NMR, or C NMR? The absorption is around 3,000 wavelengths. So that's the CSP2 and the hydrogen, and the double bond, the A ring group, is around between 1,500 and 1,600. Now, if you're talking about HNMR, hydrogen NMR, carbon NMR, just depends. Now, for hydrogen is 6.5 to 8, or 1.5 to 2.5. So 6.5 to 8, meaning that the protons are highly deshielded. And then when you're looking at the benzylic ring, it's somewhat deshielded. Now for carbon NMR, it's going to look at that CSP2 or the I ring group. That's going to be between 120 to 150 ppm. So a little bit higher on the spectrum. Now, we was talking earlier, like a lot of times benzene and bromide, they kind of like each other. They have this little bit of a romance going on. So you can have that. And so these are absorptions of dibromobenzenes. You can have different ones of those. Okay, so you got your O dibromobenzene. And so you got 3 types of carbons, 3 NMR signals. Your M is going to have 4 types of carbons, 4 NMR signals. And then if your bromines are in your para position, it's only going to be 2 types of carbons, and it's going to be 2 signals. So it just depends on where the bromines are and how they're going to give out the signals. So O going to give off 3, M is going to give off 4, and then para is going to give out 2. Now, what about these? Now, I am going to tell you something. Benzene, toluene, the xylenes, it's several of you guys going to be taking classes at the C Lab this summer, right? Several of you guys? I'll take it, right? Last year, last summer, a house or several houses kind of burned down over there on the island, caught on fire. Toluene itself, definitely benzene and toluene, is in a lot of building materials, It burns really nasty. It catch on fire fast, quick, and it burns nasty. So just fair warning. So a lot of the houses that are at the beach, they burn quick. And if they really close up together, it'll jump and it'll just catch on fire real quickly. So a lot of building materials are made of toluene. So they are simple. They are obtained from petroleum refinery. They use for starting materials for synthetic polymers. So like paints, they are in there. So that's why I was saying. Now, if you put them in things, so to get octane ratings to boost them. That's what you put in there to boost your octane ratings. You put benzene or toluene in there. Now, if you got compounds that got 2 or more benzene rings, they're called polycyclic aromatic hydrocarbons. So naphthalene, mothballs, that is the simplest one. That's the active ingredient in mothballs. That's what gives mothballs their smell. So you got benzene, toluene, xylene. Now, benzoapyrene. Now, that is a common PAH. It is found in cigarette smoke. So when you inhale it, that's what gives you the actual cancer in cigarette smoke, in tobacco. That right there. Now, what happens is it's the incomplete oxidation is not fully completed. So that's what is found in the cigarette smoke. Now, when they are oxidized, they're cancer causing. So that's what that is. Now, are there other synthetic ones? There are plenty out there. They can flex, twitch. So this is helicine, and that's what it does. It can bend, it can flex. It has a lot of chirality to it. So it can really do a lot of things. So this one, Twistoflex, that's what it can do. So helicine, Twistoflex, it can do a lot of things. It's non-planar to reduce the stereo interactions. They're chiral. They don't have stereogenic centers. So these are synthetic ones. And this is where people have really played with the shape of it and got them to twist and bend. Now, are there drugs that contain benzene rings? Yes, there are. Novocaine. So for those of you that get your teeth pulled, all of that stuff, root canals and all of that, that's in Novocaine. Zoloft, for depression, panic disorder, Zoloft. It has several benzene rings, so these are one. And Virucept, that's an antiviral drug used to treat HIV. That's one of the more popular ones that are out there right now. Now, how about benzene and its stability? How does that happen? How do we make it stable? You can have hydrogenation of cyclohexene, 1,3-cyclohexadiene and benzene. You can all three give cyclohexane treated with XX hydrogen in presence of a metal catalyst. However, for benzene is much less predictive, and you can see that right there on the screen. So if you can take hydrogen over palladium catalyst, that's what you can do there, and you can get your delta H formation, so your interpure formation. For the first one, it'll be a negative 120, so it's giving out for somewhat amount of heat. The next one, negative 232, that one is about the most. And then when you do benzene, it's in between those two. So with benzene, it is a lot more stable. Now, let's talk about all three of those when you talk about heat or hydrogenation for benzene. Now, benzene is lower in energy, and that it can't be explained based on the resonance structure. And that's what it is, the stability of the hydrogen compound. And basically what's going on is, it's just like when you have your, let me see what I think about, your diatomic molecules. it doesn't want to release. It likes being in that structure. It likes being in that structure because it makes it stable. In order to get it out that structure, you got to make it unstable for it to break apart. Now, like I said, it doesn't like addition. It'll substitute because it just like that ring structure because of the stability. Now, what happened? Its behavior is not limited to hydrogenation. It does not undergo addition reaction, typical. It doesn't react to yield an addition product. You got to have this fluid acid, bromine substitutes. It yields a product that retains the benzene ring. It loves the benzene ring. It doesn't want to get rid of it. That's what it does. Additional product would no longer contain a benzene ring. So it won't contain the benzene ring, but a substitution will. So you can substitute it, but an addition product is not going to contain it. So like for this one right here, one of those double bonds is going away and the bromine is just right there. So when it's substituted, it still keeps the benzene ring. Now, we've been talking about aromatic. So what does it take for a structure to be aromatic? It got to be cyclic. That's just the main thing. Now, what it is, every p orbital got to overlap with the other p orbitals. Everything got to overlap. It got to be in cyclic form in order for it to be aromatic. If it doesn't overlap, like you see here, hexa 135 triene, there's no overlap, so it will not be an aromatic. So this is the criteria. 1, it gotta be cyclic. 2, it gotta be planar. It gotta be in a plane. Now, adjacent p orbitals must align so that electron density can be delocalized. So here, this one is not aromatic. That's the shape of a stop sign. It's a 2-shaped 8-member ring. Then you got your adjacent p orbitals. They cannot overlap. The electron can't delocalize. Now, what you can do to make it delocalize is non-planar and non-aromatic. It can undergo the addition reaction just like the other alkenes, and then it can become something like that. Now, number 2, the molecule must be completely conjugated, meaning that it must have a p orbital on every atom, meaning that it's a p orbital right here on each one of them. There's no p orbital there on those 2. It's not aromatic. This one right here, because that p orbital is missing there, is not aromatic. Got to be completely conjugated, meaning that it got to have that p orbital on each one of them. Now, the third one got to follow this Huckel's rule. Now, it got to have this certain number of electrons. Now, this is the equation for it. 4n plus 2 pi electrons. N can equal to 1, 2, and so forth. Cyclic, planar, and completely conjugated compounds that contain this are especially unstable, and it's going to be anti-aromatic. Now, benzene is aromatic because it contains the 6 electrons. Now, cyclobutadiene is anti-aromatic and it's unstable because it contains 4 electrons. Even though it has 4, you still got to have those 4n plus those 2 pi electrons. You got to have that. It got to satisfy Huckel's rule. If it don't satisfy it, it is not aromatic, it's anti-aromatic. Now, here's a chart for that. Now, what satisfy that rule, if you got n equal to that, you got to have 4n plus 2. So you got to have 2, 6, 10, 14. Basically, when you do that, you got to add 4 to each one. So if it doesn't have that, it doesn't follow that rule, it is not going to work. It's anti-aromatic. Now, what's the difference between the three? How do we classify the compounds? If it's aromatic, you know you got pretty much a benzene ring. That's pretty much what it is. Cyclic, planar, completely conjugated with the electrons. Anti-aromatic is cyclic, it's planar, completely conjugated compound with electrons. Anti-aromatic, it's just missing one or two. It's got the 4N, but it doesn't have the +2. Now, not aromatic or non-aromatic, it lacks one of the following requirements: being cyclic, sorry about that, being cyclic, planar, and all of that stuff. So it lacks some of that. Now, what about your large aromatic rings? You got some that are larger. Aniline are the ones that are really big. It's a single ring that alternates the double and single bonds. And so it is named the same way, but you put the number of atoms in the ring in brackets and you add the word aniline to it. So these are really big. You got all different type of shapes for the aniline.
Okay, so that number, Dr. Jones,
Yes.
like the number in the bracket, that's the amount of carbons, correct?
Yes. Uh-huh.
Okay.
So
Okay.
right here, 4N plus 2, 4 times 3 plus 2, they say that it has 14 pi electrons and it's aromatic. So if you count around that, do you count 14 carbons? Yeah, it's 14. So
Okay.
exactly. Mm-hmm.
Okay.
Oh, glad you could join. All right, now, for
Yes.
color rules for that one. You got some of these that have the 10 pi electrons, but a planar molecule. Sometimes you can have these structures, they can be so big, they can buckle or puckle to relieve the strain, because they can get big. And so 10 aniline is not planar. It cannot be localized over the entire ring. So with that one, it's not aromatic. So you got most of these that look aromatic, but the one with 10, it won't, and it will buckle. So you have some of these that can be big, but they can buckle under pressure. And so they won't be aromatic. Now, what about the ones that are fused together? Because you got the ones that are fused together to form the PAHs. Now, there are different ways. So naphthalene, anthracene, and phenolphthalein, they got 10 pi electrons. This one got 14, and you see how this one is hooked up. It's got 14 too. They just joined differently. And so with these benzene rings, like I was saying earlier, they burn differently. They smell badly. So that's the thing that you can notice about the aromatics. Aromatics, the smell of them. They have those rings. That's another reason for the names, the way that they smell. Now, resonance structures. Now, as the ring increases, the numbers of resonance structures increases. Now, naphthalene is a hybrid of 3 resonance structures, where benzene is a hybrid of 2. So good old mothballs. Gotta love grandma's closet. Because my grandmother's closet smelled like that. So what about heterocycles? They contain oxygen, nitrogen, or sulfur. They can also be aromatic. Pyridine, I work with that a lot in my research. It can smell. So oxygen, nitrogen, or sulfur, aromatics, smell. There's one thing you can think about them as that. not only by their carbons and their shapes, but pyridine. We use that a lot in making different things. And so it still have the resonance structure, and it has the 6 pi electrons that are in there. So another one, pyrrole is another example of an aromatic heterocycle. It contains a 5-member ring and 1 nitrogen atom. The p orbital or area adjacent atom, so it's completely conjugated. It has 6 electrons, 4 from the bonds and 2 from the lone pair. It's cyclic, it's planar, and it's completely conjugated too. Even though it doesn't look like it, it actually is. So it's an aromatic as well. Now, let's look at the two and the differences in the two. Now, non-bonded electron pair is localized on the nitrogen atom. Now, in pyro, however, it's non-bonded, it's in the p orbital, and it's delocalized over the ring. Now, in this case, when you look at pyro, the entire ring is electron rich. But whereas if you're looking at pyridine, most of the electron pairing is focused around the nitrogen. So it just depends on where it is. So with pyridine, it is focused just on the nitrogen, but in pyro, it's over the whole ring. And you can see the electron density here in red versus the electron density around everything else. Now, you can have biologically active heterocycles. So histamines. So what we like to take, because now we got pollen in the air, we like to take antihistamines, right? So it's found in many tissues. So it's aromatic heterocycle with 2 nitrogen atoms. One similar with the N atom of pyridine and similar to pyro. So histamines basically is kind of a combination of those two. And if you look at it right here, this one got this 5-member ring. One is there, and it still got the hydrogen off of there. So that's how that looks. So histamines. So that's what causes us to act up when we have our allergies and all of that stuff. And we have to take the antihistamines to actually calm it down. So histamine, keep that in mind. Make sure you know that. Hint, hint. Now, you can have aromatic compounds that are also ionic. Now, let's talk about that. You can have them that they can be negatively charged and positively charged if it has all of that. Now, this is a cyclopentadiene anion. Yes, you can have that because something can join right there. All sp2 hybridized, you still got your 6 pi electrons, and then you can draw different resonance structures because that pair right there and that charge can go anywhere on that ring. And so you can have them there are ionic aromatics. You can have those out there. Now, are there different cyclopentadiene compounds? Yes, they are. You just have to have the right ones. Now, sometimes they can be aromatic, anti-aromatic, and non-aromatic. Just depend. Now, the 5 resonance structure can be drawn for the cyclopentadiene cation and radical. Only the cyclopentadiene anion has 6, a number that satisfies Huckel's rule. Now, if you got one that got 4 pi electrons, it's anti-aromatic. And then the 5 pi electrons, it doesn't contain either one of those. It's an odd number. Basically, it's non-aromatic. So, cyclopentadiene itself is not aromatic because it's not fully conjugated. But Cyclopentadiene is much more acidic. And so hydrocarbons, because of the conjugate base that is there, is aromatic and becomes very stable. So what happens is the conjugate base of it is stable than it itself, and it's more acidic. Now, you can lose a proton and cause the cyclopentadiene anion to become fully conjugated and aromatic. So that's how you can actually form it. So you can have cyclopentadiene is not aromatic, but if it loses a hydrogen, that's what happens. It becomes that. So it becomes stable. Okay, so the next one, trophilium cation, is planar too, and it got a positive charge. It got a 7-member ring. So this is a cation. So you don't see the anion. Now you're looking at a cation. This one the same way, completely conjugated, got the 6 electrons. It satisfied the Hooker's rule. So with that, so you see here is just completely satisfied, and then it even have the p orbital right there that is vacant. So it satisfied the rule. So let's talk about that rule. Why do we care about this? Why does the number of electrons really determine this? You got to consider orbitals and bonding. We're going back to orbitals and bonding in general chem on this. So why do we care about this? Cyclobutadiene, only 4 pi electrons, anti-aromatic. Now, what benzene, 6 pi electrons, aromatic. How do we account for this? So they cyclic, they planar, they completely conjugated. But why it has to be that? Why? That is the main question. And we go back to molecular orbital theory. We're going all the way back. Valence bond theory. So I talk about this in chapters 8 and 9 in the book that I use for 202. So valence bonds theory is inadequate for describing systems with many adjacent p orbitals that overlap, and in this case, the aromatic compound. But molecular orbital theory permits a better explanation, meaning that it describes the bonds as the mathematical combination of atomic orbitals and then molecular orbitals. And a molecular orbital occupies a region of space in the molecule where the electrons are most likely to be found. So looking at this is basically saying that, okay, molecular orbital theory can give you that idea of these can be found in these certain area. The electron density, where the molecules, where those electrons are mostly concentrated. So when we look at electron density, that's why we have to look at molecular orbital theory. Where is those electrons going to be? At what time those electrons going to be there? So molecular orbital theory accounts for that. Now, if you go back, how do we form these molecular orbitals? Keep in mind, you got a set of n atomic orbitals that form n molecular orbitals. If 2 atomic orbitals, they combine, the molecular orbitals are formed. Now, in order to have an aromatic, you guys, it is based on the p orbital overlap. Now, there are 2 lobes on each of the p orbitals. They are opposite in phase with a node of electron density at the nucleus. When 2 p orbitals combine, the molecular orbitals should form. So that's what they're saying. That's the best way to really explain this. If you got 2 p orbitals, if they overlap, if they combine, that's where the molecular orbitals can form. Now, in that case, yes, that makes a lot of sense. Now, you can have bonding and anti-bonding orbitals. Now, go back to general chem, and that should have been talked about in there. I know that's been a while, but that's where it's at. You can have constructive or destructive, meaning that when the combination of two p orbitals, they can be constructive to whereas they can join together, they kind of double up. But you can have them where they are destructive, where they are opposite acting, and they can basically cancel each other out. And so this is what you see here. Light phases interact, and then when they combine, you got increased electron density between the nuclei. So you see that. Now here, when the opposite phases interact, they basically just cancel each other out, or they going back to being the same thing. So really no electron density. So that space in between them, where here they are joined. So you can have a bonding orbital, or you can have an anti-bonding orbital. In this case, bonding right here, anti-bonding there. Now, two p atomic orbitals can combine to form two molecular orbitals. So that makes sense. The bonding molecular orbital is lower in energy than the two p orbitals. Now, when you have something that anti-bonding, they don't want to be there. They're going to be higher in energy because they're destabilizing. And so that's going to push the nucleus apart, and then they're going to be in opposite phase. So that's what happens. So here, because they are working together, it's going to be lower in energy. They are stable. And then when they're pushing each other apart, they are higher in energy. So that's what happens. Now, molecular orbitals. All right. So when you got molecular orbitals and you got benzene, they're much more complex than two molecular orbitals form. And we're going to see that that's in figure 15.8. Since each of the C carbon atoms of benzene has a p orbital, 6 atomic p orbitals combine to form 6 pi molecular orbitals. So they're labeled, what is that, 5-1 to 5-6. 5-1 is the lowest in energy. They keep going up. You got your 3 bonding orbitals, and you got your 3 anti-bonding orbitals. So that's what happens. So it basically balances out to where you got 3 anti-bonding, 3 bonding orbitals. And see, that right there really accounts for the addition and substitution that it don't want to add to it, because you got anti-bonding that is in there, but it would do substitution. So that is what's going on. We don't want to do the addition because it got the anti-bonding and then orbitals. And then for the bonding, it'll do the substitution. So it just depends on which one. And that's what makes benzene sometimes to be selected. Now, these are the different types of molecular orbitals for benzene. You guys can see there, highest energy there, anti-bonding. So you see those, and then these are your bonding ones right here. Now, the most important feature for the 6 benzene rings when it comes to molecular orbitals, the larger number of bonding interaction, the lower in energy the molecular orbital. So bonding, that's helped with stabilization. So that's helped. The larger number of nodes, the higher in energy. So that's what it is. 2 pairs of molecular orbitals with the same energy are called degenerate. And then you can have the highest energy molecular orbital, or HOMO, and then you got the lowest unoccupied molecular orbitals, that's LUMO. So that's what you saw right here. So LUMO right there, HOMO right there. So you saw those. Now, so how can you predict whether something is aromatic? So you have to look at the polygon. And then what they do is look at which one have the highest energy, equal energies right here, equal energy there. And then one got the highest energy, one got the lowest energy. So that's what they look at. So you draw the polygon in question inside the circle with its vertices touching the circle. Mark the points at which the polygon intersects with the circle. That's very important. You got to make sure it's intersects. and then draw the horizontal through the center circle and label the MOs as bonding, non-bonding, anti-bonding. And so you go on from there. MOs below this line are bonding. The MOs at this line are non-bonding, and the ones above the line are anti-bonding. And so that's what they did. At the bottom is bonding. Bonding MOs are filled. Anti-bonding are at the top. So that's what they do. The total number are always equal to the number of vertices in the polygon. When they do this, this is another way to check for Hunkel's rule. They're always one lower energy bond, and then that's what they do. So this is just a double check. So that's what they use. Here, they can do the same thing for a 5-member ring. They can do it for a 7-member ring and do the same thing and make sure. So that's what they did. So they can do the cyclopentadiene anion, the trophylum cation. They can do the same thing for those as well. Okay. Now, what about the patterns? What about the molecular orbital patterns? So Hunkel's rule, right here, you got 4.0 equal to 2 electrons. Here, 4 plus 1 equal to 6. 2 plus 4 is 6. 2 plus 4 plus 4 here is equal to your 10 and then 14. So they must completely fill with electrons. So the magic numbers for them to be aromatic gotta fit the Hunkel's rule. So that's what they say in here. 2, 6, 10. Basically, you just added on 4. Is the way it's looking. So that's what it is with the pattern. Now, let's talk about carbon and everything. So carbon got allelotropes of what? Diamond, graphite, and what else? Diamond, graphite. You got your plain C. Yeah, those are the 2 allotropes. So there's a third one technically that's supposed to be out there. We'll talk about that in a minute. So diamond is got an infinite array of 6-member rings, covalently bonded. You got graphite. You got benzene rings too. It goes in 2 dimensions. So graphite, our pencil legs that what we write with, is in 2 dimension. Diamond is in 3 dimension. That's the difference between the 2. Now, the molecular structures are very different, but they got carbon in it, and so they got those particular structures. Now, these are sheets of graphite viewed on edge, so that's right. Graphite is in planar sheets of benzene ring. They're held together by weak intermolecular forces. So when you write with a pencil, that's why the pencil lead breaks up quick. It's because of that, because the graphite is in those planar sheets. Now, I said there was a third one, Buckminster fullerene. That's what they call that. This was founded at Rice University. Richard Smalley actually found this. I actually met him. He won a Nobel Prize in chemistry for discovering this. And he is called one of the fathers of nanomaterials this day. Several of his students, one of them actually I worked with at Auburn when I was there. And so a lot of her research deals with this form of carbon. Now, they call this the buckyball. So if you've heard of it, they call it the buckyball. That's the nickname for it. It is completely conjugated. It has 60 carbons in it. Got 20 hexagons, 12 pentagons joined together. This is what they discovered there at Rice. And so basically, they compare it to a soccer ball. That's what they compare it to. It's really a soccer ball. So it undergoes addition reaction with electrophiles as ordinary alkenes. That's what make it so special. And that's been the debate for years with this. Is it an aromatic? If it's not, it fits the criteria for aromatic. And so that's why people have done a lot of research with the buckyball. A lot of stuff. Can we do this to it? Can we add functional groups to it? So back in the early, I'll say 2000s, when I was coming out of grad school 10 years ago, this was the big research thing. This was the big thing. This was what everybody was working on between that. And can this answer the call for making rechargeable batteries better? So everybody been looking at this. So that's been the question that everybody's been trying to answer, is whether or not it's aromatic. And there's two schools of thoughts out there. Some people say it is because it does follow the Humphrey rule. And some people say, well, technically it's not because it can do this addition reaction that regular benzene can't do if it's by itself. So it's two schools of thought. When we go to meetings, a lot of people like to argue over that, but it's out there. But this is considered the third allotrope of carbon. So that's what it is. So we know diamond and graphite is the main two. This one is quickly becoming the third one. Okay, this is it for chapter number 15. When I see you guys on Wednesday, we will do chapter number 16. We will have a test online very soon. Be looking for quizzes from these chapters. Since we're going to be taking the quizzes online, we can't do the redo, quote unquote, test. So I'm going to put quizzes for each chapter online. Study those, look at those very carefully. You will have a couple of attempts to do those chapter quizzes. So make sure you study those, because those questions will come back up on your exam. Like I said, for the labs, the ones that we have not finished, what we are going to do is basically, I found some of those labs on YouTube, and I'm looking through the ones that I like and don't like, but I'm going to put the links to those. You guys just write your reports based on that. The videos are going to be very short. They're going to be anywhere from 5 minutes to probably no more than 20 minutes. So I don't want you taking up a lot of time. With that, they just gonna, I'm gonna put them there, and they're gonna be due just the same every week. Now, if you want to go ahead and take your time and go ahead and do them all up, I'll have them open. So if you want to do all the labs at one time, just knock the labs out of the way, perfectly fine with me if you want to go ahead and do that. If you want to do them week by week and just keep it like we've been doing normally, the only difference is we just not meeting in person, that's fine too. Questions? How are you guys doing? Y'all staying safe? We're not conjugating around people. We're keeping our distance.
Yeah. No more than 10.
Okay. Right. No more than 10. Okay. Other questions? You guys are good?
I had a question.
Yes.
We did not do chapter 14 like in class. So I was wondering when we were gonna.
Oh, I can do it next class. Not a problem.
Okay.
Not a problem. I'll go back and do 14. Let me know that.
Sydney, you took notes?
Huh?
What?
You took notes, Sydney?
No, because it's empty. See? That's how I knew. I was like 14, and then I got on and it was 15. I was like, okay.
Okay. Well, we will do 14 next class. Next class.
Why am I dinging? What is going on?
Okay. All right. We will do 14. So you guys will have an exam coming up very soon, because what I am going to try to do is try to do pretty much a PowerPoint every class. and I'll try to finish up early. If you guys have questions or anything, feel free to email me. What I am going to try to do, because I don't know if they're going to tell us to fully shut in or whatever. I don't have my kids here right now. They are gone. But if they do have to be here, just be mindful. They will come and pop up on the video and everything. So I want to give you fair warning. I'm trying to keep them away, but the 3-year-old, I can get him to settle down. The 2-year-old, he'll want to be on the camera. So just be mindful if they tell us to totally shut in, that they will have to be here. And he likes to get a little rambunctious at times. Both of them do. Other than that, at night, I would probably come on after they go to bed or when I have them down for nap, because I'm going to go pick them up in a few minutes. And I will have a separate meeting number for office hours, and I will send that out to everybody. So if you got questions or anything, I'll probably be on Zoom and I could answer those questions. So I'll probably do it during their nap time for about an hour, and then I'll do it late at night when they go to bed. So it'll probably be after 9. So it'll be probably between 9 and 10:30. So I'll probably be on and just be on Zoom if anybody got questions or anything. And Aaron, I will work on trying to get my board clearer. I think I can just move my camera and see if I can move it closer to the board. You guys, because I got this set up at home, since you guys are here, you guys can see my board, right? Y'all can see it. Travis, can you see my board? Can you see what's on the board? Barely. Can you see what?
I cannot.
Okay, I just have to move the camera closer because I got a camera on tripod, so I can move it closer. So that's not a problem. I can adjust that. So if we have to use the board, you see, I got one here, and I'll just move my camera closer and everything so you guys can see it. I was just trying to try it out because I know I'm going to need it for some of my other classes. So, okay, you guys, I am done. You guys stay safe. For the ones that did not join, I will have a recording of this and I will post this. So if you need to go back over it, you can. You guys also have your PowerPoints there as well. So if you got any questions, email me, let me know. Anything else before I get off?
Okay, thank you, Dr. Jones.
Thank you so much.
Not a
It's
problem.
good seeing you guys, although it's remote.
Yes, good seeing you guys. Yes,
Yes,
it
yes.
is. Okay, you guys have a good one. Talk to you later.
All right.
Bye.
Bye.
Bye, guys.